Welcome to Innovation Alley. In this episode, host Dave White is joined by experts from Wade Trim and Aqua-Aerobics for a discussion on PFAS and the regulatory drivers and emerging technologies aimed at treating and destroying these forever chemicals.
Hello and welcome to Innovation Alley. I'm Dave White, our wet weather practice lead at Wade Trim. We're really excited to be here today in Rockford, Illinois, continuing our conversation on wastewater treatment, in particular the world of emerging contaminants and PFAS. What are engineers, what are equipment suppliers doing to help tackle this challenge right now? We're going to learn about it today. With me is my co-host, Vin Rubino.
I lead the water wastewater treatment practice for Wade Trim.
I'm John Dyson. I'm our product manager for our cloth media filtration technology and our new Aqua-PRS technology for PFAS removal.
Hello, I'm Terry Reed. I'm the Director of Research and Development for Aqua-Aerobic Systems.
And I'm Natalie Betts. I am the lead of the Wade Trim PFAS Task Force and also our Atlanta office lead.
So to kind of set the stage for PFAS, I understand it's a part of a number of constituents called emerging contaminants. Vin, could you tell us a little bit about that?
Sure, emerging contaminants by definition is something that just came up. We just discovered it's a problem, we just discovered it's our water or our wastewater, and now regulations are developed to address that. So PFAS, as Dave mentioned, is kind of the poster child of today. A few years back, it was endocrine disruptors, which came from pharmaceuticals and personal care products. And then there was microplastics, which is still an issue for us now in our water and wastewater. So we find them, we discover them, we find out they're harmful, and now regulations are developed to address that. Regulations come technologies, right? So now you have emerging technologies to cover these contaminants. We'll be talking about some of those today. So the regulations come to address it. In Florida, House Bill 1379 is an advanced wastewater treatment regulation covering the standards, actually. It's nitrogen, phosphorus, and BOD and TSS. There are other tertiary treatments required for these emerging contaminants and other contaminants that we'll come across all the time. So we'll be talking about some of those today. And we talked a few podcasts ago with Dr. Glenn Dieger about one water, which means that drinking water, wastewater, stormwater, they're all connected. And contaminants get recycled amongst these three environments, and it's the circular water economy, or CWE. So we'll talk about some technologies today to address these emerging contaminants.
Yeah, as Aqua-Aerobics, we've been in the business of innovating with lots of our technologies for a long time. I mean, we brought cloth media filtration to the marketplace in the 90s, and over that time frame, we've continued to advance that technology, expand the application range. That we can apply that technology from not just a tertiary application for basic filtration in a wastewater plant to we've moved to industrial applications of tertiary treatment. I head up cloth media filtration for more of the high solids applications, which is advanced primary treatment. But also for storm and water treatment, wet weather treatment, those type of applications. But we've also been working with our technology and other areas, as mentioned earlier, looking at endocrine disruptors, utilizing cloth media and combinations there of technology. But we've also, taken that same knowledge and expanded it to other areas. And our Aqua-PRS technology, which is specifically designed and was designed to handle high strength waste of PFAS concentrations and reduce those levels down dramatically to drinking these new drinking water standards that are there. Terry probably can talk a little bit more.
Yeah, so the We've been involved with treating microcontaminants for about 15 years. We initially were looking at using membrane bioreactor technology, and we worked with the Colorado School of Mines to identify if there was any sort of absorption or removal in that regard, and kind of waiting for the legislation or regulations to get to a point where it would allow us to put the technology in place. That didn't come around. However, fast forward a few decades, and our partners in Europe are, through the EU Water Framework Directive, are actually having now to look at those constituents. And I believe, for wastewater treatment, they look at an 80% removal across the wastewater treatment system. So we've had the opportunity with our filtration technologies to look at using some type of absorptive technology, such as granular activated carbon or powdered activated carbon, and then following up with filtration to remove those residual microcontaminants. The PFAS issue for us came about in 2015, and at the time we weren't quite sure exactly how to approach that, because we knew the adsorbent requirements would be much higher to remove PFAS. They're much smaller compounds, more difficult to remove. And we had some prior work with microadsorbents in removing taste and odor compounds in drinking water applications, and we thought, well, maybe there's an opportunity there to use a microadsorbent that we knew would work at an accelerated rate versus granular activated carbon and powdered activated carbon. So we started that, and some of the work that had been done at NC State suggested that it would be effective to remove PFAS. However, the limitation at the time was you probably would need a concentration of this microadsorbent to an extent that would be difficult to filter out. So we gave some thought to how to do that and developed this Aqua-PRS technology, which instead of carrying, say, 50 or 250 milligrams per liter of microabsorbent, this technology allowed us to treat 25,000 or hold 50,000 milligrams per liter of this microabsorbent to have this greater relationship of microabsorbent to PFAS to affect those removals. And so that technology was really kind of combining a couple of different approaches. There are, of course, separations technology like nanofiltration and RO, which work quite well in PFAS removal. There are destructive technologies, and there are absorptive technologies like granular activated carbon and ion exchange. So the technology we developed was a combination of absorptive and separation. So we would use a microabsorbent to tie up the PFAS, and it wouldn't settle by itself, so we'd have to have a filtration device to separate that out. The clean water would go downstream, and then we would retain these high concentration of microabsorbent to affect the PFAS removal. So that's really the approach that we've been taking with regards to PFAS.
Where does that research stand now, Terry?
So the proof of concept testing began, like I said, in about 2015. We did some work in the lab, had our successes and failures, and came to a layout that we're currently using now. We developed a prototype in conjunction with the Colorado School of Mines. They did some testing on AFFF waste water, and it worked quite well. And from there, we developed a series of pilots. And we've been doing pilots at different places across the U.S., including the Brackish Groundwater National Desalination Research Facility. And more recently, we completed a project with the Department of Defense on as part of the Environmental Security Technology Certification Program, or ESTCP. And in that case, we use this technology to treat both surface water and groundwater at very high concentrations. The surface water was somewhere around 5,000 nanograms per liter of PFAS, and the groundwater was about 40,000. In that work, when we were doing that, the big part of the big question we had was what the regulations were going to be. At the time, they were 70 nanograms per liter as a health advisory level for EPA, for PFOA and PFOS, but we knew down the road it was going to become more difficult. So we targeted at the time a 40 nanogram per liter combined of the UCMR3 compounds, those 6 compounds that include PFOA, PFOS, PFNA, HPA, and PFHXS, I believe. And so we were successful in that, in demonstrating that technology. And through additional pilots that we've created, we are now at the point where it's in the commercial realm. So we've passed that technology development level where we are commercially promoting the technology.
And maybe just to take a step back, I had eggs for breakfast at the hotel this morning in a nonstick pan, and I was thinking about this podcast. I was wondering, is there PFAS in there? I mean, Natalie, you head up our PFAS task force. We've started to learn. I mean, you guys have been working on PFAS research for years, but we're trying to get up to speed on it because we have clients that are facing these issues. And I mean, maybe just in general, where does PFAS come from? What is it?
Yeah, so PFAS is a type of chemical that has some very valuable characteristics. So it has a hydrophilic end and a hydrophobic end, and the hydrophilic end can attach well to surfaces, and that can be clothing, it can be pans, it can be carpet, furniture, and the hydrophobic end repels both water and oil. So that's a really valuable characteristic in manufacturing. And another great thing about it is that it doesn't wear off, which also on the flip side makes it very persistent in the environment, so it doesn't break down. So the PFAS that has been manufactured, it's all still here. Whether it's on a product, whether it's in the environment, whether it's in water, all of the PFAS that has ever been created is still around, because we're still working on figuring out ways to treat and destroy PFAS. So PFAS came from industry. It has been in the environment since, it's been in consumer products, I think, since the 1940s. And we're getting to the point where we're able to detect it in water, and realizing when we've done some research and studies and finding that it can be quite toxic. So that's brought us to this state of working on ways to treat it.
And Terry mentioned a lot of developing the technology from a technology and equipment standpoint. You recognize something's there, said, well, let's develop something to do something with that, right? Treat it, remove it, destroy it, whatever it is. Natalie and I and Dave on the consulting end, we need to be able to advise our clients on how serious is the problem, what technologies are available to do it, where is it in your treatment system, and where do we put the technology to remove it or destroy it. And Natalie's doing some work at the water tower to address one of those items.
Mm-hmm. Yeah, I can talk more about that. Something I forgot to mention this, but you mentioned before, these are the questions that consumers are coming up with. So as consultants, we are serving our clients. Those are a lot of utilities and municipalities. They're getting those questions too. So our role in serving our clients is helping them to be ready to address those questions when they come up. And what Wade Trim has done to pursue that is to develop this PFAS task force that I'm heading up with Vin's assistance and a handful of other folks in Wade Trim. And it's supported by the Office of Applied Technology. And the goal of the PFAS task force is we have two goals: research and communication. So our first goal includes research on PFAS, and what that's going to look like is we're partnering with the Water Tower, which is the Global Water Innovation Hub where Wade Trim's Atlanta office is located, and F. Wayne Hill Water Resources Center, which is co-located with the Water Tower right next door. We can see it out the windows. And then a professor and graduate student from the University of Alabama who have an NSF grant for PFAS research. So these three entities, Wade Trim, the Water Tower, and the University of Alabama, are going to collaborate on research at F. Wayne Hill Water Resources Center. So we're still in the development stages of this research. But what it's going to look like is taking samples from F. Wayne Hill, analyzing them in the labs at the Water Tower, and then compiling this data and looking at where are we seeing PFAS in the treatment train, And also, it's we'll have developed kind of a template for utilities to follow. Like if you want to test your facility for PFAS, here's one way it's been done. Here's how it went. It kind of gives you a step up. Kind of a starting place for doing that research. And then our second goal is communication. So we're going to be communicating both internally at Wade Trim so that the folks in Wade Trim know what our capabilities are, and then communicating externally to let the water industry as a whole, including utilities, including our, teaming partners and anyone who's related to the water industry, to know the results of this research so that we as a water industry can take steps forward in learning about and learning how to treat PFAS.
Yeah, and I know we're looking at, collaborations, and trying to figure out, with something as new as this, what do we do? How do we treat it? And that's where you guys come in. You're at the forefront of research and looking at these things and implementing these technologies.
And I think that's a really valuable tool to have in terms of, we know that there are different concentrations of PFAS and different constituents within the PFAS, as well as co-contaminants, that there isn't going to be one technology that fits every case. So being able to evaluate and assess those technologies and help guide people in terms of determining which technology best fits their needs, I think is really important.
Yeah, and that's help we need. You guys are the experts on it, and we certainly appreciate that.
I would add, in that area, Terry and I have been working on the research side of developing the technology, and we initially started out focused at the high concentration levels, thinking, the market, the limits would be in certain areas. Of course, EPA's recent proposed drinking water levels are much lower. Okay, it's really going to change the economics in our industry of where we're going to have to do treatment. Okay, my role as a product manager is really partnering with Terry and his group in the research and development side to now commercialize and bring the product to market. So I'm the kind of the middleman between the engineering department, who's going to engineer the standards, the vessels, the systems that are there, to the process side, and how that integrates to the marketplace, along with the commercial activities of introducing it to the marketplace, doing pilot tests, which we do a lot in our industry, to demonstrate as much as R&D work as Aqua's done already. Our industry has, and I've been in this industry a long time, we still depend tremendously on pilot tests. People want to touch it, feel it at their facilities. And so we will be going out demonstrating at other facilities, like possibly at the water tower and other places, out across this country, eventually probably around the world, where we're demonstrating the technology, how effective it can be. So when you're doing this, it's a vast process. It's very systematic. I've introduced several products over my career, and it takes a long time for us to adapt technologies into the marketplace, to build that data, to build the installation bases that are there to show it that it's a proven technology. But it all starts initially with the R&D work that's there.
So John, Terry also mentioned that you started with attacking a high amount of PFAS. You have several different trains going on in terms of potential product lines to address different levels of PFAS or different applications for products?
Yeah, the technology that we've developed is very versatile, and Terry, I'm sure will add a little bit more. As he mentioned, the range of absorbent that we can utilize is a pretty vast range, and we're even talking numbers that most people don't even think about when we talk, at 5,000 milligrams or 10,000 milligrams. As he mentioned, 40,000 milligrams per liter. That's not typical that we've done, but because of that variability, we can design the system specifically for the type of water. The concentrations that are there, which means it can be applied across a vast range of applications. to a drinking water plant as maybe just treating a water that's already filtered, that's really clean already, but still has PFAS in it, to maybe eliminating filtration, okay? Doing pre-treatment to an RO system, treating the brine waste from an RO system, already doing PFAS removal. The wastewater plant, where would it possibly be fit in the wastewater plant? Classically, you think at the back end of the treatment facility. The industrial applications are enormous because the pre-treatment, I think, industry is going to have to do in the future where certain wastes were acceptable coming into a treatment plant, now won't be, because I think wastewater plants will be pushing back on the pre-treatment side to industry to prevent PFAS from entering their facilities. And that means there's going to be a lot more complex and robust treatment for PFAS and other constituents coming into wastewater plants, limiting the impact on the wastewater. So it's going to be a very broad area, and the beauty, I think, of our technology is the ability to vary the concentration based on the water matrix that's coming in, along with being able to achieve very low levels of PFAS out of the system, or in most cases, non-detects.
And I think the complex nature of PFAS will ultimately tie in multiple technologies depending on the makeup and the concentration. Maybe on the back end of a wastewater treatment plant, it's a lower concentration, maybe a single technology will work. But as we start to see people put in reverse osmosis systems, for example, which will be highly effective in removing PFAS, but creating a stream that's of concentrated PFAS. And so looking at maybe a technology to remove PFAS and reduce the amount of waste on the RO reject, all the way to John's point, if we work upstream and find the industry that's potentially putting out very high concentrations, maybe it's a couple technologies that include GAC or ion exchange and the Aqua-PRS or different versions of it. But it's something that I definitely think is a case-by-case basis and does require not only piloting at each site, but benchmarking to make sure that the technologies that are being looked at, which is the right one for the application.
So you'd even be able to work with industry, like catching PFAS before it gets into the environment, rather than trying to filter it out when it gets pulled into a water treatment plant. So like on the tail end of that manufacturing process that produces PFAS, your technologies could be used.
Yeah, it could be used there. As Terry mentioned, airports, military bases was some of our initial markets, okay? And that's, to me, almost like industrial pretreatment when you think about those installations. Other areas that we're working on are stormwater runoff, as Terry mentioned. Airports have major issues with PFAS as it relates to runoffs. Industrial facilities have the same thing. As you mentioned earlier, microplastics, okay, are a big issue, and we've sold several filter systems for removal of microplastics for industry, the regulations in some areas. But this PFAS is actually going to probably cross across that type of aspects too, because a lot of industrial sites that may have microplastics may have PFAS issues. It's an ever-growing area when we think about those type of materials that are out there and how the solution. And we continue to do research not only in what we're doing now, but other areas of how do we address stormwater runoff. It's a different challenge in itself, because when you have stormwater runoff, now you've got a lot of solids in the water, okay? How do we prevent, the PFAS from getting in if it's intermixed with the solids? Well, that means you have to generally going to have multiple steps to take out the solids, then do the treatment for the PFAS. So there's going to be a lot of combinations, and depending on the industry and their given needs, their loads and levels, it combines biological treatment processes or other things there too together.
So how far away are we from using this equipment somewhere?
Well, that's interesting. We've been working on it a while. We're starting to do commercial pilots now from that standpoint. So if you follow our general industry, once we go do pilots and have successful pilot studies on a commercial level, usually projects follow right after that. So I would say in the neighborhood, would expect to have, probably projects that are in design within 6 to 9 months. And of course, the standard schedule to actually design the facility and implement. There are some other opportunities that may come quicker. We would expect that we would probably have operating installations within the next 18 months or so, have the first one.
You make an interesting point too about microplastics. That's an area that we've been looking at for a number of years in terms of the definition of microplastics are any particles between a nanometer and 5 millimeters. So, it's a broad range in terms of defining the plastic, and we've been looking at it from a standpoint of we can filter that material, but there haven't been any regulatory drivers to put the technology in necessarily for that. But now with the PFAS issue, we're finding that some of the plastics are actually constructed with PFAS in it. Some are, like for example, the textile industry coated with it, and then they break down, and now we're dealing with polyamides or polyester fibers that have this material in it. And then there are some plastics that will actually absorb the PFAS. And the problem being is that as this enters into our natural systems and it's adjusted, it can change within the body, within aquatic species or even the human gut in terms of desorbing some of the PFAS, and now it becomes a problem. So even though microplastics haven't been necessarily regulated to the extent in terms of numeric quantification, we do know that it may tie in terms of PFAS limits. So filtration technologies or separations technologies that are effective on microplastics may allow some wastewater treatment plants to get to that point where they're meeting these drinking water standards of 4 nanograms per liter for PFOA and PFOS. So it's really a dynamic issue that we're having to solve, and again, it makes us have to look at many different approaches to solve each individual issue.
So believe it or not, we're getting close to the end of our time. So want to kind of close it out with thoughts on PFAS, where it's going. Maybe start off with you, John.
Yeah, it kind of go into some of the opening statements. For me, the one water concept is important, okay? As we move forward in terms of as an industry, we have to think about that our drinking water is our wastewater. In many places that's true. I personally know over my career of facilities that their streams at 100% the water source downstream to a drinking water plant. Even though it's not direct, it's indirect, reuse. And thinking about that and making sure that we are doing everything from our standpoint by providing technologies that are cost effective, that allow utilities to implement, make cleaner water, dispose of these contaminants within the process are going to be essential. And as a manufacturer, our job is to continue to innovate, develop new things as we see the future vision of constituents that need to be removed.
Terry?
Yeah, I think it all comes down to just paying attention to the regulations and where they're going, and have a technology that's sustainable for the municipalities and industries that have to deal with it. And at the end of the day, it's all about waste minimization. We don't have necessarily, a single solution to solve the problem, but again, using multiple technologies or finding a way to reduce the problem to a manageable size that would allow destructive technologies to work very effective, I think is where we're going to see most of our efforts going.
Right, Natalie?
Yeah, I'm just excited to see, now that we have these draft standards from the EPA for drinking water. I'm excited to, we finally got a regulatory driver. That's something that we talked about. And now that we have this driver, I'm excited to see where industry goes in helping utilities meet those standards.
I always say water treatment is not stagnant, and we've developing technologies all the time to meet challenges. Who knew we have a new challenge? We now have technologies that Aqua-Aerobics is working on to help treat these emerging contaminants. And if the next one comes out, I'm sure you're going to start developing it in this center, in the R&D center, and then John's going to bring it to market.
It's the plan.
All right, well, great conversations today on PFAS and emerging technologies. Thanks for joining us. We'll see you on our next podcast.